Divergence. I'm going to actually give you an idea what this name come from. Divergence actually measure the tendency of the fluid to connect all these birds at a point. Okay, so I actually have a picture over here. So what's the tendency? It goes away from this point or going toward this point. Okay, it's divergence. Okay, so use divergence, and it is a scalar. Okay? It is a scalar. How is that defined? Okay, so it is defined it this way. It's going to be the partial derivative of the first component of this vector field with respect to x, and then adding the partial derivative of the second component here with respect to y, and then adding the partial derivative of this third component here with respect to z, and you just sum that up. The result of this is a scalar. Okay, it's not a vector. Okay, so it should be equal to a number. Okay, so curl is a vector field, and then the dip, we call it dip. Dip is a scalar field, so it's a real number. Now, in terms of the gradient operator, okay, or the del, okay, the divergence of F can be written symbolically as the dot product of del with F. Okay. So do you guys remember last time for curl, how was it defined? Curl is the del, what was the product between del and F for curl at that time? It was a cross product, okay? And diff over here, the divergence here, is the dot product, okay? All right. So that's something interesting to remember. Let's try to use this example to feel more comfortable with the diff, the divergence of this vector field. So we're given this vector field here, and let's try to find diff of this vector field. So using the definition above, okay, let's do it together. We will have the del dotted with F. So we take partial derivative with respect to x of which function over here? What should I put in the first? Which function should I put inside this parenthesis? Yes. So that should be the component function on the I, right? So that should be xz. The second one over here should be xyz. Okay. And then this one here should be this negative y squared for the k. Okay. And then when you take the partial derivative over here, okay, and then you just do the differentiation, okay? Take the partial derivative, and then you should come out with z plus xz. Okay, that is the diff of f. Okay, what's the physical meaning of this? It actually measures the tendency of the liquid, like going away or going toward a point. Okay, so that's the diff. Okay. So if the F here is a vector field on R3, then curl is also vector field on R3, right? Remember, curl is a vector field, okay? And as such, we can compute its divergence. Remember, you can compute divergence of a vector field. So curve of F is also a vector field. So we're going to compute the divergence. Okay, so, and it turned out that when you compute the divergence of the curl of F, if F satisfies this condition, which means the F here is a vector field on R3, and P, Q, and R have continued second order partial derivative, then it turns out that the divergence of the curve is actually equal to the zero scalar, zero number. Okay, the result of the divergence is a scalar, is a number. So this is just a number. So that's kind of interesting. Let's look at the proof. It's not too long. Okay, how do we prove it? We just use the definition. So we're going to. So the divergence of that is going to be the del dotted with this vector, dotted with the curve. Okay, so I'm going to put it right here. So this curve over here is this one over here, right? Okay. So is the del dotted with that? That's the curve, okay? And then now, what should we do? Then we should compute this one first, right? To compute this one, remember we set up the determinant of that 3x3 matrix, right? And then the first component will be this, second component will be this, and the third component will be this. And then now, because you're taking the dot product of del with this, then you take the partial derivative of the first component here, and then take the partial derivative with respect to x. And then you take the second component of this, to this one, and you take the partial derivative of that with respect to y, and then take the third component of this one, and take the partial derivative with respect to z, and you sum them up, okay? Now, and then when you do that, you come up with this result here. And let's see the cancellation, how does it work, okay? How does the cancellation here work? So this one over here is going to cancel with which one? Is it this one over here, right? This two. Remember by root theorem, the order you can partial derivative here doesn't matter, can switch it, right? So this two actually cancel, okay? And then also, what else you can cancel? This one and this one here cancel. What else can cancel? And then this one and this one here get canceled. So the result here will turn out to be 0, okay? So this is kind of interesting. So if the vector field each component has continuous second order partial derivative, which means that, what does it mean? Which means that all of this are continuous, okay? All of them are continuous right here, okay? Then what happened is the divergence of the curve is equal to 0, okay? Equal to the number 0. And here is an analog with this scalar triple product, right? So remember in the past, we talked about scalar triple product right here. So what's A dot A equals B? What's A dot A equals B? Remember the scalar triple product, what does it represent? Do you guys remember? Yeah, the volume of what? Parallelepiped. Yeah. You know what I mean, okay. Okay, so remember last time we talked about if you have this, right? This is A, and then this is B, and then this is C. Then it's going to be, hey, but any case. Okay, so A dot B cos C, well, anyway, that's the scalar triple product, right? Scalar triple product. And that represents the volume of this parallelepiped over here, okay? The magnitude of this. The magnitude of this is the volume of the, it is the absolute value of that, right? The result here is a scalar. Okay, so the absolute value of this should be the value of the parallel pi. Okay, now if you have A dot A cos B, okay, what happened to A cos B? When you do the right hand rule, A cos B is that be perpendicular to A and B, right? So this is A cos B, right? Okay. And then we started with A. Remember the dot product is kind of like, what's the shadow? The dot product is like the shadow of the A or this one projected down to this A. Okay. Remember that product is like the, so remember you try to do A dot B, right? So this is A. Okay, just say this is A and this is B. Then A dot B is going to be what, say this angle is theta, is what? The absolute value of A, the magnitude of A times magnitude B times what? Is cosine, right? Times cosine of theta. So A times A here times cosine theta is actually this one over here. So that is the shadow. Okay, that's the shadow of this A. Okay, that's the shadow of that A over here. So when you have A dot this, so this one here is perpendicular to this. The shadow of this on this A, it should be zero, right? So this is the way I'm here. Or you try to think about this. So what happens to this? Then you can show a parallel pi. Then let's see how the parallel pi look like. So you're going to have this A, right? You have this A. Try to use this A right here. And B, you have B over here. And then the other one is also A. The other is also A. Then the parallel pi has no height on it, right? Because this three vector here, they're on the same plane, right? They are coplanar, right? They're on the same plane. So there's no parallel pi. So the value for that should be zero. Okay. Yeah. So now the analog between this one and this one here, right? This is the dot product. Okay, dotted with this one cos this. Okay. It's like A dot A cos B, and this is del dot del cos F, which is out here is zero. Okay, so there's an analog with this. Now let's try this example over here, example 5. So that this vector field can be written as the curl of another vector field. That is F does not equal to curl of G. Okay? At first, say, what are this? Okay, now let's try to think about what's this. So that this cannot be written as the curl of another vector field. So F cannot be written as the curl of a vector field. That's interesting. Okay. How can we do that? Let's think about. Can you guys think about it? Even though I'm actually here, take a minute to think about it. What happened? Well, it's hard to prove it directly, right? So we can try to prove it by contrapositive, by contradiction, right? So a lot of the time when you try to prove that directly is hard, you can try to prove the contrapositive of it, okay? So we can try to assume that F can be written as the curl of another vector field, okay? So this is my proof by contradiction. Okay. So remember, you say if A then B, then the contrapositive is if not B, then not A. So we can try to show that this is not true, okay? And then we'll come up with a contradiction. Then we're able to prove that this has to be true, okay? So that is the plan, okay? So I'm going to try to say that this one over here is not true. In other words, that F could be written as the curve of another vector field G, okay? Then what happens? So if this is true, then what happens? We'll have the diff. Remember the theorem we just have above? When you take the diff of a curve, what happens of a vector field? What's the I didn't cover this. Okay. When you take the diff of a curve, what's the result? For the same people, that should be equal to 0, right? So the diff of a curve of any vector field here, when they have continuous second order possibility, is always equal to 0. So that should be equal to 0. The diff of a curve of vector field equal to 0. Okay. So that is equal to 0, right? Remember this thing here above, right? This one, right? The diff of a curve of a vector field is equal to 0 if I have second order possibility. Okay. So if this is true, if F here is the curve of G, then diff of that is equal to 0. But what does diff of F equal to 0 mean? Well, is diff of F here equal to 0? Well, we're given this vector field, right? What's the diff of this? Let me cover this. Okay, I'm going to cover this. Okay, so what is the diff? What's the diff? How do we calculate diff? It is del cos or dot. Dotted with this, right? So this should be del dotted with F, right? Which means you're going to take the partial duality of the first component with respect to X, and then adding the partial duality this second component with respect to Y, adding the partial duality of this with respect to Z, right? Okay, so, okay. So what's the partial duality of this with respect to X? You get Z, yeah, you got it. Okay, let me just write it down here, okay? So you should get Z, okay? And then you're gonna add partial duality of the second component here with respect to Y. What is it? XZ, yes, you got it, okay? So that should be XZ, okay? And then you also add partial duality of this with respect to Z. What is it? It should be 0 because there's no Z here, right? That's independent Z. So plus 0, okay. Now let's see this one. Yeah, so it is Z plus XZ. Okay, the diff is equal to this. Does it equal to 0? No, it doesn't, right? It doesn't equal to 0, right? It doesn't equal to 0. So, but then here it says, suppose the F here is the curve of G, and we come up with this equal to 0. So we have reached a contradiction, right? So that is going to contradict with this, okay? So a contradiction. So this cannot be true. So our assumption here cannot be true, okay? So F here cannot be written as a curve of G. So this is an example of a proof by contradiction. Okay. All right. Now, I have some Chinese here, but let's see the picture here. Okay. This one here, the diff over here is greater than 0, and then it goes out, right? Then the tendency to go out, okay? And when the diff over here is less than 0, it goes in, okay? So it goes in, that one. It's equal to 0, it would be like this, okay? That one, the diff. Okay. Again, the reason for the name divergence, did I say that right? Divergence. That looks like the same name as the series divergence and convergence. Okay. Anyway, the name divergence can be understood in the context of a fluid flow. Okay. So if f of xyz is the velocity of say like a gas, okay, then the diff of it represents the net rate of change with respect to time of the mass of gas floating from the point per unit volume. Okay, the diff of that measures the tendency of this to diverge from the point. Okay, so I guess the name divergence here comes from the diverge, right? So it diverges from the point. Okay. If diff of f is equal to 0, then f is said to be incompressible. Okay, incompressible. So here's a picture. So this one over here is the diff, and then this picture here is for the curve. Okay. Oh, the reason for the interpretation of diff of f will be explained at the end of this divergence thing. Okay, now so far we have two differential operator, right? So we actually have the curve, and then we have the diff, right? Okay, and then we also take the diff of a curve. Okay, now we're going to compute the divergence of a gradient vector field. Okay, now this time it's going to be diff of the del, the diff of the del right here. Okay, so remember the diff, okay, is going to be the dot product of whatever vector you have in here. So we're going to take the del dotted with this vector over here. So take this, okay, and here, dotted with that. And then what does this do? This one here says that you're going to take each component of this, and then differentiate with respect to x, and then differentiate with respect to y, differentiate with respect to z, and you sum them up, right? Okay. Now, so that is this one, okay? And this expression occurs so often that we abbreviate that as the del, right? Del square f, okay? This operator, kind of the del square over here, is del dotted with del, del dotted with del. Okay, it's called the Laplace operator. Okay, because it's relation to Laplace equation. Many weeks ago, okay, we talked about the Laplace equation. Laplace equation is this. Okay, this one. The second order partial derivative. Okay, sum this up and equal to 0. Okay, so that's called the Laplace operator. We can also apply the Laplace operator to a vector field. Okay, so you can do the vector field. You take the first component, second component, and third component, and each one you're going to take so you take the first component, and you take the second order partial derivative with respect to x, and you get this. Take the second component, and then take the second order partial derivative with respect to y, and you put it here. Then you take the third component function, and then take the second order partial derivative of that with respect to z, and you put it over here. Okay. Okay. The last part here, we're going to talk about the vector form of Green's theorem. Okay. So do you guys remember Green's theorem? What was the Green's theorem? Okay, let me remind you here. Green's theorem over here is if this curve is positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continued partial duality on an open region that contain D, and most of this will be satisfied, okay, in this. Then what happened? Then this single integral, this line integral over the curve C is equal to the double integral here over the region D. And how are they related? D is, the C here is the boundary, and the D is the region that enclosed by C, okay? That's D right here. So that was green theme, right? Okay. At that time, I color code this. I said this is a P, and then this is a Q. So yeah, so you have this. Now today, we're going to have the vector form of green theme. I'm actually going to bring this up right here. All right, so you're looking at this part over here. This over here is, remember, this is the same as this, right? This line integral over the curve, okay, this one, the dot part out here and this, they mean the same thing, the line integral, right? Now, if you're looking at this one over here, remember last time we talked about, this one here has only the vector field has only two components, right? The I and J component. And the third component is equal to 0. And in the beginning of this class, right, I told you guys to compute the curl of that when you replace the third component here by 0. And you guys told me that it turned out to be this, right? Now, if you're looking at this, does it look like the green theme, this part over here, right? It looks just like it, right? So, except this one has a K in it, right? It is a vector. This one doesn't. So, how can you get rid of the K? Then you can dot it with K itself. So when you dot this with K itself, then you will take this and dot multiply with 1. So when you take this one, dot it with K, then we'll just get, because K dot K is just 1, okay? So you will just get partial derivative Q with respect to X, subtracting partial derivative P with respect to Y, and which is exactly what you have over here. So now we can replace this, this part over here by curl of this F dotted with K. This is the same thing, okay? Curl of that dotted with K is just this, which is this one over here, okay? All right, so this is green theme in vector form, okay? So, so this line integral over the curve C is equal to the curl of the vector field, okay, dotted with K and then dA. Okay, so that's the vector form. And what does this one do? This equation here expresses the line integral of the tangential component of F, okay, the tangential component of F, because it dotted with the dr, right? Okay, along C as the double integral of the vertical component of curve F, because you dotted with K, so you consider the vertical component of curve F, and then over this region D. Okay, and the region D here is enclosed by the C. Now I know today you have a lot of new definition. Yeah, you might get your head spinning. So what are they? But it takes a while to digest. So sit down and think about it. Okay. We're going to define a similar formula involving the normal component of F. Okay. If C is given by this vector equation. Okay, so suppose this curve over here. Okay, so we have this curve over here. RT is equal to this. T greater equal to A, less than equal to B. Then this line integral of f dot n, remember the n here is the normal, is the normal vector, okay, the normal vector of the curve, okay. So the normal so when you dot it with n, what's f dotted with n? So if the force dotted with n, so you want to see, suppose you have force going this way, dotted with n, that means take this force here. What will be the component in this direction, in this normal component? Okay, so that's the one. And then ds here is this one. Okay, remember that? Okay. All right. So the normal vector here, the unit normal vector, is this one. So when you dot it with this unit normal vector, you will get this. And when you do the simplify it, you're going to turn out to be this. Okay. Now this one over here, looking at this, so what is it? Can you guys think about this one here? Kind of look familiar, right? We have the f over here is actually have, what is this f here? The f, let me write it down. So the f vector field has this 2, right? This is the first component in the I, and then plus the Q and the J component, right? So this one over here, what does it do? You take the first component, differentiate with respect to x, and then adding, take the second component, differentiate with respect to y, and what operator does that? The diff or the curve? Which one? This one. It is the diff, right? Remember the diff? The diff is you take the first component and differentiate with, take the partial derivative with respect to x, right? And then you're adding, take the second component and take the partial derivative with respect to y, and then you sum this up. So this one here is the diff of this f, okay? So we have this second vector form of Greensian, okay, like this. Now, so here's the Greensian. So we put them all three together, okay? So here is Greensian, here is another vector form of Greensian, and here is a second vector form of Greensian, okay? All right, and that's the end of this. Let's do a recap, okay? So first, we state what we have, okay? So diff and curve. So roughly speaking, divergence measures the tendency of the fluid to connect or disperse at the point, and the curve measures the tendency to swell around the point. And divergence is a scalar, okay, while curve is a vector, okay. Now the next one, okay, let's do a recap. See how much you guys remember, okay. So the easiest way to remember the curve of F is using this determinant of this 3x3 matrix, right? With IJK putting here, what will be the second row? Operator, yeah, the vector differential operator, right? So partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, okay? And what should I put in the last row? PQ and R, yeah, PQ and R, okay? And then that will be the curve of that, right? Okay, next one, if the vector field has only this 2 component, the last component will be 0. what will be the curl of this vector field? Then you have Penny. It will be only this last component because this two will become 0. Yeah. So it will be only this. Yes. All right. Next one, the theme. You guys can remember. If f is a function of 3 variables that has continuous second order partial duality, what is the curl of the gradient of f? What's the curl of the gradient of f? Yeah, that's equal to 0. Yes, you got it. Okay, that's equal to 0. The curl of the gradient of f is equal to 0. It was proven. Okay. Now, if the vector field is conservative, then what happened to the curl of it? Yeah, that's equal to 0. Yes, that's equal to 0 because of that. Okay. What does it mean conservative? Conservative means that could be written as the gradient of f. Okay. This can be written as the gradient of another function f. Okay. Okay, so that's equal to 0. Okay, next one. There are 2 ways today we mentioned to verify that a vector field is not conservative. Okay, can you remember what are the 2 ways? Yeah, it shows that the curl is not 0, right? Because if the curl is not 0, then it's not conservative. Yeah, so that's the first one. So we can try to show that the curl is not equal to 0, so this is not satisfied, then it's not conservative. So that's one way. Okay, what's another way to do it? This one, okay, yeah. Right? Okay. Okay. Do you remember? I think that was 16.3. That was the video I made. So it was one homework. Actually, I mentioned it earlier today in class. So it had to satisfy. Yeah, right. It satisfied this. Okay. So partial duality P is subset Y should be equal partial duality P is subset X. And then also this has to equal this. All 3 of them have to satisfy in order for the field to be conservative. Okay, if it has 3 components. If I only have 2 components, then we only need this. Okay, so if a vector field has only these 2 components, then we only need to verify. Actually, this is actually necessary condition. If it's conservative, all of this has satisfied. Okay. Right. So if one of this is not satisfied, then it's not conservative. Okay, good. All right. So show that one of that is not satisfied. Okay, number 4. One way to show that the vector field is a conservative vector field. So this one here show that it's not conservative, right? We just saw one of this is not satisfied. Now, what about if we want to show that it's a conservative vector field? How do you do that? Number 1, you have to show that the curl equals that. Yeah, you have to show that. Number 2, what else we need? Oh, yeah, yeah. So show that the function is defined on all of R3 or a simply connected region, right? So if you can show that the function this vector field is defined on all of R3, or maybe this simply connected region, okay? And if the curve here equal to 0, then it is a conservative vector field. So you need this one first, right? But you also need this to define on if it's defined on all of R3, then you can show that is conservative vector field. Okay, so if you can do these two things, okay, so do this one first, and then show that it's defined for all R3. Okay, now when each component function is a polynomial function, it certainly is defined on all of R3. Okay, then you can show that it's a conservative vector field. Okay, and then the next one here, we also talk about how to find a function such that how to find this function small f, the scalar function f, such that the big F is equal to the gradient of f. In other words, this big F is the conservative vector field, it is the gradient of. So it's kind of like duality and anti-duality, right? So if you know the duality, how do you apply the anti-duality, right? So this is kind of similar. The relation between the big F and small f are kind of like this is the duality. So this is the duality. This small f here is the anti-duality. Right? This is kind of like the operator, like the differential operator. Remember? Okay. This kind of remind you of this differential operator. Okay, like that. So when like if you differentiate that into this, then this is the unconditional also. Okay. So to find this f, you need to integrate this to get back to this. Okay. So we actually went over the example. And what did we do last time? That was a long example. It was this one. Okay. So what did we do over here? We take we write down the probability rules from the x, y, and z, and then we take one of them and then integrate the rules back to say because this is probability rules from the x. We come up with this. And notice that you need to add a constant function with respect to x, okay, which is a function that's independent of x. So over here, this one has no x, which means it's independent of x. Okay, so you add a function that's independent of x, it only has y and z in it, and then after that, you differentiate this with respect to y, and you compare with this. Then you try to figure out what this one here is. And then after that, you differentiate that with respect to z, compare with this. And then you try to figure this. And then now you can substitute that. Okay? So that's how you find that small f. Okay. So you take anti-duality, different integrating. Okay. Next one, let's do a recap on divergent. Okay. So divergent measures the tendency of the fluid to connect or disperse at a point. Okay, divergence is a scalar. Okay, so is it going to be diverge outside or going in? Okay, so with positive, it's going to go out, and with negative, it's going to go in. Okay, so diff of f. This operator, how is it defined? Do you know, remember the definition of diff of f? What is it equal to? Take partial duality of the first component with respect to what? X, and then take the second component and then differentiate with respect to y, and then take the last one with respect to z, and then what do you do with them? You add them up. Yes, you got it. Okay. All right. So that was the diff. It is a scalar. And then diff of f, using the del rotation. Remember the del rotation? How is this one defined? Del, what's the operation? Del and f. What is the operation between them? Huh? It's a dot product. Yes. is del dotted with F. And what about curl? Is del cos with F. Yes, you got it. Okay. Now, and then we went over this theme. Okay. Then what happened to the diff of curl of F? Okay. Okay, next one. How to show that F is not the curl of another vector field? Looking at this. Yeah. So one way to show that is to try to show that the diff of that is not equal to 0. Okay? Because if this is the curl of another vector field, the diff of it will be equal to 0. Right? Okay, so yes, so that's one way to show that. Okay. Okay, next one. Okay, here is the things over here. I put a picture. Okay, so this one here, this picture here, you can try to relate to the divergence. Okay, so it's a tendency that the liquid is going to go inside or go up. Okay, and then the curl is the tendency of the going to swirl around that point. Okay, all right, and then Laplace operator. So this is del square. How is it defined? Del and del was operator between them. Either cos or dot. Cos or dot. Huh? This one. Dot. Yeah. Is del dotted with del. Okay. The divergence of gradient vector field. Okay. So the divergence of the gradient is the del dotted with this gradient. What should I put over here? This is the Laplace operator on this F, right? So what should I put over here? Here you go. Okay, so you take each component and you take the second order partial derivative, okay? And then you sum them up, okay? So this is the Laplace operator. All right, the next one. There's a lot of information today. We can also apply the Laplace operator to a vector field. So basically, you would take the second order, or you get this, right? You take each component and apply the Laplace operator. And okay, let's go to the vector forms of green scheme. What should I put over here? This. So the line integral of this over C is equal to double integral of what? Over the region D. Curl F dotted with K. Yeah, you got it. Good job. Okay. Curl F dotted with K. Okay, then another one, another vector form of the green scheme. What should I put over here? So F dotted with the normal vector, unit normal vector right here. What should I put here? And look at all the paper. And I see Kenny has all this paper like, oh, it can go all the way to there. Okay. Okay. What should I put here? Hey, look at the hint under. Divergence of F over the region. Okay, so it is, yeah, diff of F. Okay. All right. Oh, you guys did a good job today.